we've got a binomial expansion to do. So here's the formula for binomial expansion. Remember, n is a natural number here greater than 2. So I'm going to replace a by 1 and b by 2 over n, and then n remains as it is. So 1 plus 2 over n to the n is going to equal 1 plus n choose 1, which actually n choose 1 is nc1, which is n factorial over 1 factorial times n minus 1 factorial. It's just n, in fact. So it's going to be 1 plus n times 2 over n. And then I'm going to get nc2 for the next one. Do you know what? Let's also just figure this out by the side. nc2 is going to be n factorial over 2 factorial, which is just 2, times n minus 2 factorial. This becomes n times n minus 1 over 2. And that'll be times n by 2 over n squared. Got one more term to deal with. So the next one's going to be nc3. Let me do it down here. nc3 will equal n factorial over 3 factorial n minus 3 factorial. So this becomes n times n minus 1 times n minus 2, and then the n minus 3 factorial cancels out, and then the 3 factorial gives me 6. So that's what I'm going to get there. So n minus 1, n minus 2 over 6 times 2 over n to the power of 3. Let's just simplify this. I'm going to get 1 plus 2 plus n times n minus 1 over 2 times 4 over n squared. So the n and the n squared are going to partially cancel. The 2 and the 4 are going to partially cancel, leaving me a 2 there. And then I'm going to add n minus 1, n minus 2 over 6 times 8 over n cubed. So again, the n partially cancels. This now becomes a squared. Can divide each of these by 2 to leave me 3 and 4. So I'm going to get 3 plus 2 n minus 1 over n plus 4 n minus 1 n minus 2 all over 3n squared. Great. Now remember, that was just the terms up to 2 over n to cubed. This is actually an infinite expansion. Whereas to hence prove, when n is greater or equal to 3, so actually our expansion will include these and maybe some more, that we can write this down. So for n greater or equal to 3, let me just copy this down. This is what we're trying to aim towards. One plus 2 over n to the n is therefore going to be greater or equal to what we just found in part 1. Because remember, there's more terms unless n is 3, in which this is the exact expansion. So let's have a go at simplifying this. I'm going to get 2n over n minus 2 over n from this term here. Over here, I'm going to get 4 times n squared minus 3n plus 2 all over 3n squared. So this becomes 3 plus 2 minus 2 over n plus 4n squared over 3n squared. So that actually becomes 4 over 3. And then minus 12n over 3n squared. That becomes minus 4 over n. And then 8 over 3n squared. So this is 5, which becomes 15 over 3. And then I'm adding on 4 over 3 in a minute. And then I'm minusing 2 over n minus 4 over n. That becomes minus 6 over n plus 8 over 3n squared, which equals 19 over 3. We're getting there, minus 6 over n plus 8 over 3n squared. So this thing here will necessarily be greater or equal to 0. And therefore 1 plus 2 over n all to the power n is going to be greater or equal to the smaller amount, which is 19 over 3 minus 6 over n. If we know it's greater than this, then it's got to be greater than something that is smaller. And we've got to our answer. Brilliant. One more part to go. Here we define this function where x can be any real number, x is greater than 0. Given that the function f of x is continuous and that this is true, prove that f of x equals 0 has a root in the interval 9 to 10. So let's look for a sign change. We're going to substitute 9 and 10 in. Note, when we do that, x becomes a natural number and we can use our result from earlier on in part A, because that was what we relied on when we did that expansion. So f of 9 is going to equal 1 plus 2 over 9 to the power of 9 minus 3 to the 9 over 6. And remember, we showed earlier on in part A that this was true. So let me just copy this and bring it down. This was for whole numbers. So I can say that f of 9 will be greater or equal to 19 over 3 minus 6 over 9 minus 3 to the power of 9 over 6. Now 3 to the power of 9 over 6 actually becomes 3 to the 3 over 2, which is 3 root 3. So let's put this, oh, and this actually simplifies to 2 over 3. So f of 9 is greater or equal to this, which is equal to 17 over 3 minus 3 root 3. Now recall that we showed that root 3 was less than 7 over 4. So if root 3 is less than 7 over 4, then this will be greater or equal to 17 over 3 minus 3 times 7 over 4, which is equal to 17 over 3 minus 21 over 4. Let's put it over a common denominator. So times through by 4 gives me 68 over 12 minus 63 over 12, which is 5 over 12, which is greater than 0. So I have just shown that f of 9 is greater than 0. Now for f of 10. So this is going to equal 1 plus 2 over 10 to the power 10 minus 3 to the 10 over 6. I need a different tactic here because remember, I'm trying to show that there's a root in the interval 9 to 10. So I want to show that this one is less than 0. So I can't go into the same kind of ideas I had for 9. Well, 2 over 10 becomes 1 over 5. So this is 6 over 5 to the power 10 minus 3 to the power of 5 over... Wait, let's leave it as 10 over 6 for the moment, because earlier on we were told that the sixth root of 3 is greater than 6 over 5. So this is actually going to be less than 6 over 5 to the 10 minus, remember, this is a 3, this is actually the sixth root of 3 to the power of 10. So this also becomes 6 over 5 to the 10. So let me just clarify. I'm saying that because I know that the sixth root of 10 is greater than 6 over 5, then this becomes greater than 6 over 5 to the 10, which means if I'm subtracting them, f of 10 is going to be less than if I set it equal to 6 over 5 over 10. So overall, f of 10 is going to be less than 0. And then we can just finish it off. There is a sign change. And f of x is continuous over the interval. There's nothing to suggest it is not. And therefore, f of x equals 0 has a root between 9 and 10. Okay, that is pretty tough, I think, that last little bit. So well done on your efforts.